In this experiment, we will use colorimetric methods to determine the value of an equilibrium constant for a reaction. In Part 1, we will detail the experiment and collect the data. In Part 2, we will perform the calculations that are required. The objective of this experiment is to determine the value of the equilibrium constant for the formation of the ferric thiocyanate ion from iron 3 plus ions and thiocyanate ions. We will measure the concentration of the ferric thiocyanate complex colorimetrically using Beer's law. The equilibrium constant for a chemical reaction, which we will denote Kc, determines to what extent the reaction will proceed as written. The larger the value of Kc, the more the system will generate products. The smaller the value of Kc, the less products will be generated. In this experiment, we will be determining the equilibrium constant for the formation of the ferric thiocyanate complex according to the equation Fe3 plus aqueous plus thiocyanate ion aqueous, forming the ferric thiocyanate ion. There are two parts to this experiment. First, we will be calibrating using Beer's law. Second, we will determine the equilibrium constant from a known set of solutions. Colorimetric analysis involves passing a beam of light through a sample and then measuring the amount of light that passes through. To do this, we use an instrument called a spectrophotometer. Here is shown a schematic of the basic operating components of a spectrophotometer. We will go through each component one by one. The first component we need is a light source. Typically, this is just a bulb that provides light with the correct range of wavelengths for the analysis we're performing. The light then passes through what is known as a monochromator. The monochromator disperses the light into its component wavelengths, much like when light passes through a prism and shows up as a rainbow. This allows us to select a very narrow range of wavelengths for our analysis. The light then passes through a wavelength selector, which further narrows the wavelength band, and into the sample holder. The sample holder, also known as a cuvette, holds our liquid sample for analysis. The cuvette itself must be transparent to the light, otherwise it will not pass through the sample. We are ultimately interested in knowing how the intensity of the light changes as it passes through the sample. The intensity of light going into the cuvette is denoted as I0. When passing through the sample, some of the light is absorbed by the sample. The outgoing intensity is I, which is always less than or equal to I0. Lastly, the light strikes the detector. This converts the photons of light to an electrical signal, which is then output by the digital display. There are two possible outputs that can be read. First is the percent transmittance. Second is the absorbance. The percent transmittance, denoted percent T, is defined to be the ratio of the outgoing intensity I over the incoming intensity I0 multiplied by 100%. Note that this takes a value between 0%, the situation where no light passes through, all the way up to 100%, where all of the light passes through. The absorbance, denoted A, is related to the transmittance as it is the negative log of the transmittance, or the negative log of I over I0. Experimentally, the values of the absorbance range between 0, the case in which all of the light passes through, to about a value of 1. Note that the value of A can be greater than 1, but this typically leads to errors in our analysis. As chemists, we tend to work with the absorbance because the absorbance is directly proportional to the concentration. We see that A is equal to epsilon times B times C, where the Greek letter epsilon is called the molar absorptivity, B is called the path length, and C is the concentration of the compound that we are trying to measure. This equation is known as Beer's law. The path length is a fairly easy concept to understand. it is the distance through which the light travels in the sample. Another way to think of this is the width of the cuvette. In our case, as in most cases, this value is 1 centimeter, although they can vary. The molar absorptivity is a little more difficult to understand. All it really is an experimental value that tells us how much a particular compound is going to absorb. The larger the value of epsilon, the more the compound absorbs at that wavelength. The color that we see for a compound is determined by what wavelengths of light are absorbed by the compound. When a compound is white or colorless, it does not absorb any visible wavelengths of light, and we therefore see all of the wavelengths and all of the colors together. When a compound is black, it absorbs all visible wavelengths of light, and therefore we see none of the colors. When a compound absorbs only a fraction of the visible light, we no longer can see that color of light. The color we do see for the compound is the combination of the remaining wavelengths that are transmitted. This is a plot of the absorbance of the ferric thiocyanate complex as a function of wavelength. We call this type of plot a spectrum. The peak that we see shows the wavelengths at which the most light is absorbed. These are the colors that we will not see in our final solution. Looking at the color bar at the top of the plot, we see that it is the blue and green wavelengths of light that are absorbed. That means that the transmitted colors are yellow, orange, and red. Our complex, therefore, has a dark red or orangish-brown color. We can now return to our reaction. The iron 3 ion plus the thiocyanate ion forms the ferric thiocyanate complex. The equilibrium constant expression for this reaction, Kc, has the concentration of the complex in the numerator and the concentration of the iron 3 ion times the concentration of the thiosulfate ion in the denominator. The goal in this experiment is to begin with known concentrations of the iron 3 and thiocyanate ions in solution. We allow these to reach equilibrium. Then, using the spectrophotometer, we can measure the absorbance of the complex. This is proportional to the concentration of the complex. At this point, we can use the ICE table to calculate the equilibrium concentrations of all 3 species, allowing us then to calculate the equilibrium constant. The procedure for this experiment has 2 parts. Part A is the calibration. In order to use Beer's law to calculate the equilibrium concentration of the complex, we first need to know the values of epsilon and B. To determine these, we build a calibration plot. We will be making a series of solutions, each with a different concentration of the ferric thiocyanate complex, ranging from 0 molar up to 2.0 times 10 to the negative 4 molar. We can then measure the absorbance of each solution using the spectrophotometer. At that point, we make a plot of the absorbance on the y-axis and the complex concentration on the x-axis. This should result in a straight line. The slope of this line is equal to the product of epsilon times b. There is one major problem that we have to correct for. If we just mix together some concentration of iron 3+ and thiocyanate ion, the amount of the complex that is formed depends explicitly on the value of Kc. But since that's what we're trying to measure, we don't know the value of Kc up front. In order to overcome this problem, we make use of what's known as Le Chatelier's principle. This tells us that if we have an abundance of either a reactant or a product, the reaction will move in the opposite direction to use up that abundance. In this case, if we have a large excess of one reactant, then we can ensure that all of the other reactant will form the product. The concentration of the iron 3+ ion in the calibration solutions will be more than 100 times the concentration of the thiocyanate ion. This makes sure that the equilibrium concentration of the complex is equal to the total concentration of the thiocyanate that we added. Our first step is to prepare the standard solutions. The 6 standard solutions were prepared according to the table. Notice that the concentration of the ferric nitrate solution was 0.200 molar. The concentration of the sodium thiocyanate solution is 2.00 times 10 to the minus 3 molar, or 100 times less concentrated. Each solution has a total volume of 50 milliliters. Each solution receives the same amount of ferric nitrate, 10 milliliters. The volume of the sodium thiocyanate solution increases from 0 milliliters in standard 1 up to 5 milliliters in standard 6. We can now calculate the concentration of each species in the standard solutions. This is a simple dilution problem. The molarity of the diluted solution is equal to the molarity of the stock solution times the dilution factor of V1 over V2. We will look at standard 4. The concentration of the iron 3 plus ion in standard 4 begins with the 0.200 molar iron 3 plus stock solution. We then multiply this by the ratio of the 10 milliliters we added divided by the 50 milliliter total volume. This gives a concentration of 0.0400 molar iron 3 plus. For the thiocyanate ion, the stock concentration is 2.00 times 10 to the negative 3 molar. The dilution factor is the ratio of 3.00 milliliters added to the total volume of 50.00 milliliters. This gives a concentration of 1.20 times 10 to the negative 4 molar thiocyanate. Because of the design of the experiment, we expect all of the thiocyanate ion to be in the form of the complex. This means that the concentration of the ferric thiocyanate complex is equal to the concentration of the added thiocyanate, which is 1.20 times 10 to the negative 4 molar. Here we see an image of the 6 standards. Notice that as the thiocyanate concentration increases from standard 1 to standard 6, the dark red color increases. This is because the concentration of the ferric thiocyanate complex increases as the thiocyanate complex increases. To measure the absorbance of each solution, we will use the Genesis 20 spectrophotometer. This is made by Thermoscientific. These are the features of the Genesis 20. This is the digital readout. This is where we will read the absorbance once the sample is placed inside of the spectrophotometer. The cuvette we are going to be using is a glass cuvette. It will hold our sample, and the glass is transparent to the visible light. The sample compartment is the compartment to the right. It opens up, and we insert the cuvette into the sample holder. We then close the sample compartment to eliminate stray light. Prior to the experiment, we set the monochromator to 447 nanometers, which is the wavelength of maximum absorbance. Before we take a reading, we must blank the spectrophotometer. This means that we put a solution inside of the spectrophotometer that has everything in it except for the ferric thiocyanate complex. And then we set the absorbance to 0. This ensures that we are only reading the absorbance for the ferric thiocyanate complex. Since it has everything in it but the complex, we will use standard 1 to blank. Notice that we have a non-zero absorbance initially for standard 1. We press the 0 ABS button, which zeroes out the absorbance. We can now read the absorbance for each of the standards one at a time. The image shown to the right indicates that the absorbance reading for standard 2 is 0.090. The absorbance readings should increase linearly as we read each standard. Having read the absorbance for all 6 standards, we see from the data that the absorbance does increase as the concentration of the complex increases. We begin with an absorbance reading of 0 for standard 1, and these increase to a final absorbance reading of 0.745 for standard 6. This has concluded part A, or the calibration part of the experiment. Now we can complete part B. In this second part, we are determining the value of Kc. We are using 6 additional solutions to do this. Unlike in part A, we will have approximately equal concentrations of the iron 3+ and thiocyanate ions in each of the solutions. This allows for the equilibrium itself to determine the amount of the complex that is formed. It is important to realize that each solution in this part will have a different set of initial concentrations and a different set of equilibrium concentrations, but the equilibrium constant values should be the same for all of them within reasonable experimental uncertainty. As before, the first step is to prepare the reaction solutions. Notice in this case that the concentration of the ferric nitrate stock solution is equal to the concentration of the sodium thiocyanate stock, or 2.00 times 10 to the negative 3 molar for both. The total volume for each solution is 10 milliliters. The volume of the ferric nitrate ranges from 4 milliliters in the first solution to 5 milliliters in the remaining 5 solutions. The volume of the sodium thiocyanate is 1 milliliter in solutions 1 and 2, and then increases to 5 milliliters in solution 6. We can calculate the initial concentration for our reactants from the table. This is the same type of calculation as before. We will look at solution 4. The concentration of the iron 3+ begins with the concentration of the stock ferric nitrate solution, 2.00 times 10 to the negative 3 molar. We multiply this by the dilution factor of 5 milliliters added over the total volume of 10 milliliters. This gives a value of 1.00 times 10 to the negative 3 molar. Likewise, for the thiocyanate, we begin with the stock solution concentration, 2.00 times 10 to the negative 3 molar. Our dilution factor is 3 milliliters added over the total volume of 10 milliliters. This results in a value of 6.00 times 10 to the negative 4 molar. It's important to remember that we cannot calculate the initial concentration of the complex. In fact, we have to assume that it's equal to 0 at the beginning of the reaction. Here's an image of our 6 reaction solutions. Again, because each of them has a different initial concentration of our 2 reactants, we have a different final concentration of our complex, and the solutions tend to get darker as we go from solution 1 to solution 6. But please remember that even though the equilibrium concentrations are all different, the equilibrium constant value should be the same. As with part A, we now measure and record the absorbance of each solution. As we can see from the data, the absorbances are all different, indicating that the equilibrium concentration of the ferric thiocyanate complex is different in each solution. This concludes the data acquisition for part B. We have now completed the experiment. We have seen several parts of the data analysis already performed, but there are still several other steps that are needed. In the next video, part 2, we will go through the remaining calculations.